Okay, good morning. So we are headed toward the final stretch of the course. And I just want to remind you that the last assignment, the one for chapter 3, has been pushed back a little bit. So I think it's due June 16th now. So you still have a couple weeks to finish up chapter 3. And if you do finish up chapter 3 early, you can go back and do problems that you didn't get done in time back for chapters 1 and 2. So, which could actually be helpful for reviewing for the final exam. Okay. So my plan today, it'll be a little bit shorter lecture today, maybe 30 to 40 minutes. What I'm going to do is I'm going to talk about what are called reactions with chemical reactants and products. And then next time I'm going to cover limiting reactants. We'll maybe get into a little bit of it today, but we'll see. Okay. So we're in, it's section 3.6. So we're toward the end of chapter 3. So these are calculations with reactants and products. Okay, so this is a very important topic. It's something that you're going to want to really focus on. It brings together pretty much everything. We're going to do it in little individual steps, but it pretty much brings up everything. Okay, so I'm going to begin with just a really simple example. Suppose that I write the balanced chemical equation for the reaction between hydrogen and water. Okay, so gaseous hydrogen plus gaseous oxygen to form liquid water. Okay, now notice it's balanced, right? We have the same number of hydrogen atoms on each side. There's 4 hydrogen atoms on each side. And the same number of oxygen. There's 2 oxygen atoms on each side. So this is a balanced equation. So there are different ways to interpret quantitatively what this means. So one interpretation is that 2 molecules of H2, right? So that 2 means there's 2 of them. So here's an H2, here's another H2. That's the meaning of 2H2. The subscript is that they're attached to each other. The coefficient is how many of those there are. So there's 2 hydrogen molecules. And then we're going to react that with 1 molecule of O2, right? So O2, again, the subscript, the number that comes after the symbol, right? So O2, that's how many atoms are bound together. So there you go. So look what happens. You've got 4 of these hydrogen atoms at the beginning. So we're going to have 4 at the end, right? But the product is now water. So how do we write that? Well, you got 1 oxygen in a water, and then 2 hydrogens attached to it. There's an H2. But it says there's 2 waters. So now we have a second one. Okay, so what is that? 2 molecules. Remember, the molecule is the H2O. So there's 2 molecules of H2O. So not only are, let's make the oxygen a little bigger. So not only are the hydrogen atoms balanced, you've got 4 hydrogens on both sides, each side. You also have 2 oxygen atoms on each side. So that's a balanced chemical equation. A balanced equation has to have every element has to be balanced, not just 1, not just 2, but everything. So in this case, everything is balanced. In Chem 11, you'll learn that you also have to balance the number of electrons, but that's not an issue we need to deal with right now. So there's your balanced equation, right? 2 molecules, 1 molecule, 2 molecules. So notice the number of molecules changes. That's not conserved. You can change the number of molecules in a balanced equation. It's just the number of atoms of each element that has to maintain, there has to be a consistency there. Okay, again, think of this in terms of a time effect. You have the H2 and the O2 at the beginning. This is what you have at the beginning. And then this is what you have at the end, right? So it's like a sequence of events. And we're not even talking about how this actually happens. That's a fascinating aspect of chemistry, is that how do these atoms recombine? It actually ends up being a pretty complicated issue and interesting. We know a lot about it now, but we're not concerned with that in here. All we're concerned with is at the beginning, we have a certain number. At the end, we have a certain number. The material has changed. Hydrogen and oxygen, an explosive mixture that you can use to launch rockets into space. Water, something you can drink, right? So very different materials, but they're made up of the same atoms, which is kind of interesting, right? Okay, so here's a second interpretation of this. What we're going to do is what we call scaling up. So imagine that you were going to make a cake. You might put in 2 cups of flour and 1 cup of sugar. We'll ignore all the other ingredients, right? So 2 cups of flour, 1 cup of sugar, and let's claim that that gives you 2 small cakes, right? That's how you can interpret. Really, a chemical equation is like baking. That's essentially what you're doing, is you're mixing proportions together and then getting something at the end, like a little machine. Reactants go in, products go out, like a factory, okay? Now, imagine you said, I don't want to make 2 small cakes. I want to make 2 million small cakes. So, you know, you're like some big industrialist and you're making cakes that you're going to sell throughout the world. You might want to make millions of these little cakes, right? Well, you realize you're still going to use the same proportions, right? You're not going to now put 3 cups of flour for every cup of sugar, or 1 cup of flour for every cup of sugar. You're going to still keep the proportions the same. It's still going to be 2 to 1, but you got to have more, right? So what's our unit of more in chemistry? What's our unit, our large unit? It's that Avogadro's number that we talked about back in section 4. Avogadro's number is this unit that we use for large numbers of things. And remember, it was very large, right? Avogadro's number was 6.022 times 10 to the 23rd molecules. And we called that a mole for shorthand notation, M-O-L-E, not molecule. A molecule is 1 little particle, 1 little H2O. A mole is a huge number of those little molecules. So that's what we're going to do. We're going to use moles as our unit. So I'm going to reinterpret this as 2 moles of H2 plus 1 mole of O2. And that is going to give us 2 moles of H2O. So all I've done is I've scaled up the number by Avogadro's number. So notice the proportions are still the same. It's still 2 to 1 to 2. That hasn't changed. That's the balanced equation. But our formula for making these cakes is a 2 to 1 ratio. 2 of these for every 1 of those gives us 2 of the cakes. Now we're going to use moles. And what's useful for that is that based on our idea of molar mass, right? We talked about that back in section 3.42. This is the number of grams of a substance per 1 mole of a substance, right? This is something we can measure easily in a laboratory. We can just put a scale out on the table and measure the number of grams. And we have this table called the periodic table, which tells us how much each element weighs. So that gives us a way to weigh things and then combine them in the correct proportions. So let me show you an example of how we go about this. What I'm going to do is I'm going to say we have, let me rewrite the equation. I'm going to say that we have the following. We react 0.45 moles of H2 with excess, I'm going to underline that word, O2. How many moles of H2O will be formed? And then part 2, so that's A. Part B is how many moles of O2 will react. Okay, so there's 2 questions here, and we need the balanced equation for it. So notice what's given. We're given the amount of H2 that reacts. And notice the units. These are the units you will often see, the number of moles of H2. Okay, now here's the logic that you have to follow to do these problems. The equation tells us that every time 2 moles of H2 reacts, 1 mole of O2 will react. Okay, that's what that's the interpretation. Every time 2 moles of H2 reacts, 1 mole of O2. That you tell from the equation just by looking at the equation. It also tells us that every time 2 moles of H2 reacts with 1 mole of O2, you will get 2 moles of H2O, okay? Just like we would say if you had 2 moles of flour and 1 mole of sugar, you would get 2 moles of cakes, okay? Remember, a mole is a number. It's how many you have. You're counting them like a dozen, okay? And that's the interpretation right there. So what that allows us to do is a proportionality. So here's our strategy. You take the number of moles of the substance that's given. So that's the substance that's given, 0.45 moles of H2. You then multiply that by a ratio. And the ratio is the number of moles of the substance that you're being asked for, okay? Well, actually, the first substance we're asked for is H2O, so that's right there. So you look at the coefficient, it's 2. So every time that the hydrogen reacts, it gives you 2 moles of water. And how much hydrogen reacted to give you that water? 2 moles. Okay. And then if you look at your dimensional analysis, the moles of H2 cancel. You take 0.45 and you multiply it by both of these numbers. You have to multiply it by the one on the top in the numerator, and then you have to divide it by the one in the denominator. So 2 divided by 2 is 1, right? So that's easy. So it's 0.45 moles of H2O. So what that tells us is that every time 0.45 moles of hydrogen reacts, we get 0.45 moles of water. Now, why is it 0.45? Well, again, it's the same number. Every time 2 of these react, you get 2 of those. So it's going to be the same number, okay? But what about the oxygen? Part B is how many moles of oxygen will react. Now, how much went in there? But it says it's excess, which means we put a lot of oxygen, so much that we don't even need to worry about how much we're putting in. How much of it actually reacted? Again, that's given by the balanced equation. So you take your 0.45 moles of H2, that's what's given, and you say, okay, it's 1 mole of O2 for every 2 moles of H2. Where did I get the 1 and the 2? Right here. There's a 1 there, and there's a 2 there. So you're multiplying it by the one you want, and you're dividing it by the one you don't want, or the one you're starting with, because we're doing this conversion here, okay? Now you're going to take the 0.45 and multiply it by 1/2, right? 1 divided by 2. So that's 0.225. Okay, so what this tells us then is that every time we react 0.45 moles of H2, we're going to react with that 0.225 moles of O2. And that is going to give us 0.45 moles of H2O. Now notice those are decimal numbers and they're perfectly acceptable, right? Those, we said that for reasons of simplicity and for keeping in line with software limitations of how people write software programs, we generally want whole numbers for the balanced equation. But in theory, there's no reason they have to be whole numbers. It's a proportion. So I could say, look, I'm going to have a really small cake and it's going to use 1/4 of a cup of flour, 0.25 cups. And it's going to use 1/8 of a cup of sugar, 0.125 cups of sugar, right? So there is no physical reason that we have to have whole numbers. We just do that for convenience to make them whole numbers so that we can do the calculations in our head is usually the reason. And it's easier to type it out. But that's what this shows. It says that if you put in 0.45 moles of H2, you're going to put in 0.25 moles of O2 so that they react in the right amounts. And then you're going to get 0.45 moles of H2O out. So imagine it this way. Imagine I had like a little container, and this is my container with H2, and another container, and this is my container of O2. And I just had like a little tube that came out of this one, and a little tube that came out of this one. And these two tubes, they came in here into a little region that's a mixing region. What you would get out of that mixing is H2O. Okay, that's really what the chemical reaction is, right? That's actually how a rocket works. What a rocket has two tanks. One tank is for the hydrogen. It's cooled down to such a low temperature that it's actually a liquid. It's very expensive because liquefying hydrogen is a hard thing to do. It has to be really cold. And it boils off really fast because the temperature outside is much hotter. Oxygen is expensive too. Liquid oxygen is expensive too because the same thing. You have to cool it down to such a point that it liquefies and it'll boil off on its own. So you have to keep filling it up all the way to the last second. In fact, if you ever watch a rocket launch, you'll see that they're filling the oxygen all the way up to maybe about 10 seconds before they launch, and then they shut a valve off, and then it's ready to go. But they are filling it to the last minute, okay? They're going to react violently, right? So this mixing region isn't so simple, right? This has got to be something that can handle that reaction. It's got to be able to initiate the reaction. Usually there's a spark plug there that will just put a voltage on, a shock, and that will cause the reaction to start. And then you're going to get this water coming out. Okay. All right. So now we say, what are the proportions going to be? Well, we know the proportion is 2 moles of this for every 1 mole of this, and you get 2 moles of this out. That's our proportions of how much goes in and how much comes out. But it's equally valid to say that for every 0.45 moles of this, you're going to need 0.225 moles of this, and that's going to give you 0.45 moles of this coming out. Okay. The reason that we have these decimal numbers, 0.45 and 0.225, is that the people who wrote this problem said, no, we're going to put in 0.45 moles of this. We're not going to put in 2 moles. So what would you get if you put 0.45 moles, right? You do these kinds of calculations if you don't have a lot of money and you're driving a car. You say, look, how far can I get on 1 gallon of gasoline? Because I only have $10 or I only have $5. So how much gas can I afford and how far can I drive with that, right? So same idea here. You're doing sort of an economic calculation. You're saying if I put 0.45 moles of this in, how much of this one do I have to put in? And then how much of that am I going to get out of it? Okay. Now, I'm going to show you one more kind of aspect of this, which is significant, which is that we can take those number of moles that we just calculated and we can convert them to grams. And the reason we would convert them to grams is that we don't have any way to measure moles. I mean, I can't say that's exactly true. There are some methods to estimate moles, but there's no direct way to measure a mole because it's such a large number. So if you think about the number of stars in the universe, let's say it's about a mole. No one knows for sure, right? We don't know how many stars. We're estimating them, right? So you can estimate moles, but you can't really calculate them perfectly. So what we can do is we can measure mass very easily, though. So mass gives us a direct exact calculation. Well, not an exact, but a pretty good approximation. So here's what we ended up with. We ended up with 0.45 moles of H2 reacting. We ended up with 0.225 moles of O2 reacting. And we ended up with 0.45 moles of H2O produced, right? That's how much you get out of it, right? So suppose we then said, convert these to masses. And remember, masses are typically in grams. They could be in kilograms if it's a lot of it. It could be in milligrams if there's a little bit of it. Medicines are typically in milligrams, right? Because they're too small to be in grams. So an aspirin tablet is, I don't know, 0.6 grams or 600 milligrams. An ibuprofen tablet is 0.2 grams, which is 200 milligrams. But when you get down to like some really powerful chemicals, they're so powerful, they're so strong, they have such an effect on the physiology that they're not even in milligrams, they're in micrograms. So you might find that there's 60 micrograms, right? Which is 0.06 milligrams or 6 times 10 to the minus 5 grams, right? So they can even be in micrograms. As far as I know, there aren't many drugs that are in nanograms, at least not yet. But some drugs are very powerful, so they're definitely in the micrograms, okay? All right, so let's convert them. How do we do that? Well, converting from moles to grams, that's something we covered in 3.4. We look up our periodic table. There's our molar mass for hydrogen, 1.01. There's our molar mass for oxygen, 16.00 grams per mole. So let's do it. We have H2. So H2, the molar mass, you just say, hey, it's H2. So there's 2 hydrogens. Each one is 1.01 grams per mole. So there you go, 2.02 grams per mole. Okay, what about O2? Well, 2 times 16. That's 32. So when you hear 32 grams per mole, that's O2. O is 16, but O2 is 32. That's the molar mass of oxygen. H2O. When you do these, you start memorizing them. You start knowing them for sure. Hydrogen's 1.01, and then oxygen is 16. So you get 18.02. Okay, so those are our molar masses. How do we use molar mass? Remember, if you're going from mass to moles, you divide by the molar mass. If you're going from moles to mass, you multiply by the molar mass. Okay, so mass will always be larger than moles. Moles is going to be smaller than mass. Okay, so let's take a look at it. So let's do hydrogen, 0.45 moles of H2. I'm going to see, we're going from moles to mass, so we're going to multiply by molar mass. So times 2.0, oh, I'm sorry, I put H2O. We're doing H2 first. 2.02 grams of H2 per mole of H2. Okay, so 0.45 times 2.02. And you get about 0.9. I'm going to round it to 0.91. Look at how the units work out. You got grams of H2. So in other words, if we had 0.45 moles of H2 reacting, we would put in 0.91 grams. That's how much we would have to put in order to react. Okay. There you go. So let's do the second one. So the second one was the O2. We decided that 0.225 moles of O2, sorry, that's not easy to read. 0.225 moles of O2 are going to react. O2 is 32 grams per mole, so we're going to multiply it by 32 grams per mole. Okay, so look again, the reason we're multiplying is to get rid of the moles and to get it into grams. So 0.225 times 32, and you get 7.2 grams. Okay, so that's kind of interesting too. Look at the big difference in mass. See how much oxygen you have? 7 grams, and the hydrogen is less than a gram. It's a big difference in ratios of masses, right? So what that means is when they do these rocket launches, the oxygen tank has got to be able to handle a lot more mass than the hydrogen tank does because the oxygen weighs so much more, okay? Now, let's do the last one, water. There's not enough room down here at the bottom, so I'm going to do the water up here. What did we decide? We decided that 0.45 moles of water would be produced, so 0.45. And again, we're going to multiply that by the molar mass, 18.02 grams. Okay, so your moles will cancel, and you're going to get around 9 grams or something like that, right? 0.45 times 18.02, and you get 8.1 grams of H2O formed. Okay, so this is actually something that we could measure. We could put in 0.91 grams of H2, put in 7.2 grams of oxygen, allow them to react, and then we would find that 8.1 grams of water is actually produced. Note that the amount of water in mass is equal to the amount of hydrogen and oxygen in mass that reacted. That's the law of conservation of matter. The mass of something that's reacting plus the mass of the other thing that's reacting has got to equal the mass of what's produced, the amount that reacts. Okay, so the amount of hydrogen that reacts plus the amount of oxygen that reacts in grams is going to be equal to the amount of water that's formed. 7.2 plus 0.9 is 8.1. They're going to be equal. That's the law of conservation of mass. Okay. So I kind of took you through the whole idea, right? That we use the balanced equation to figure out the number of moles, and then we can convert it to mass if we want to. Often the type of problem you're going to see is they give you the mass of something, and then you got to figure out how many moles it is, then find the moles of the other substance, and then convert that into grams. So let me show you a little example from Alex. So this is the problem which is called using a chemical equation to find the moles of product from moles of reactant. So using a chemical equation to find the moles of product from moles of reactant. Okay, so there's your problem. And so in this one, it's kind of long. What they do is they say wine goes bad soon after opening because ethanol. So this is a word problem. So they're going to give you ethanol, CH3, CH2OH. So that's the formula. I wrote it wrong, sorry. CH3CH2OH. Okay, so there's 2 carbons, a total of 6 hydrogens, and then 1 oxygen. Okay, so that's ethanol. Reacts with oxygen. And then they tell you that's O2. You should know that oxygen is O2. If you see a problem where it says that oxygen is reacting, put O2. To form water and acetic acid. And then they give you the formula of acetic acid. Okay, so here's what you're going to do. You're going to calculate the moles of acetic acid formed by the reaction of 0.90 decimal 90 moles of ethanol. Okay, so notice they don't even say anything about the oxygen, the amount of oxygen. That's the next section. That's 3.7, where they give you the amount of both reactants. If they only give you the amount of one reactant, that's section 3.6 is what we're doing. And for your calculations, in terms of the calculation, you can ignore the substance. They don't tell you how much there is. So the fact that they don't tell you how much O2 is reacting, just ignore it. You don't need it in terms of figuring out the amount of products. In 3.7, you'll need it. So here's our first step. First, you got to have the balanced equation. So don't do any calculations until you have the balanced equation. I don't know what this balanced equation is going to look like, but let's see. Okay. So our reaction is ethanol reacts with oxygen gas. So ethanol that's a liquid plus oxygen gas is going to react to give you water. Water is a liquid, of course, and acetic acid. So actually, let me write this out. Acetic acid is this. And they tell you it's aqueous. So remember, aqueous, they actually told you. I'm sorry, I didn't write it down here. Aqueous means dissolved in water, okay? So you got the ethanol, which is a liquid. That's reacting with oxygen. And that's going to form liquid water and aqueous acetic acid, okay? Let's see if we can balance it. I'm going to do the carbon. Carbon's already balanced. There's 1 carbon, 2 carbons. 1 carbon, 2 carbons. So carbon's already balanced. The number of hydrogens, there's 3 plus 2 plus 1. So add all those up. That's 6. Add these up. 3, 4, 5, 6. Hydrogen's already balanced too, right? And then oxygen, there's 1 here plus 2. There's 1 here plus 2. So everything is balanced. There you go. This is called, this is fermentation, right? This is fermentation. Actually, no, it's I'm sorry, it's not fermentation. Fermentation is where you take glucose and you turn that into ethanol. I'm sorry. But this is a byproduct of fermentation. So yeast will turn, and bacteria will turn glucose into ethanol. And then if there's oxygen present, the oxygen will react with the ethanol and make acetic acid. So there's your acetic acid. So it's the oxidation. So you'll see this, right? If you take wine and you open it up and leave it out in the air, after a while, it starts to taste more and more and more sour and more vinegary. That's because the ethanol is getting converted into acetic acid, right? So it's important for people that are making wine to make sure that there's, very little oxygen in that wine bottle. Otherwise, it's going to start to turn into vinegar. Alternatively, if you want to make vinegar, you just take some wine and leave it in the air. Okay. So now we've got this balanced equation. So now what does it say? It says that we have 0.90 moles of ethanol, and we want to calculate the moles of acetic acid. So how are we going to do that? Step 2, you do your calculation. Okay, so let me show you how to do that. You have 0.90 moles of ethanol. That's the piece of information they give you. So you're going to write that down. 0.90 moles of ethanol. CH3, CH2OH. You want to know the moles of acetic acid. Well, you use the balanced equation. So you multiply it by 1 mole of acetic acid. That's the one you want, divided by the one you're given. Okay, so the moles of the one you're given are going to cancel, and you're going to be left with the moles of the one you want, which is the acetic acid. So 0.90 times 1 divided by 1 is 0.90. Okay, let's convert that to grams now. The last step is to convert to grams. Okay, so we have 0.90 moles of acetic acid. So I'm going to write that here. Okay. All right, let's do carbon. Carbon is 12.01 grams per mole. Hydrogen is 1.01 grams per mole. And oxygen is 16 grams per mole. Okay, so let's find out the molar mass of this compound. We have 2 carbons, so 2 times 12.01. 4 hydrogens, so 4 times 1.01, and 2 oxygens. Okay, so that's what, 24 plus 32 is 56, so it's 60. And then that's what, 0.06 grams per mole. So there's your molar mass. So now, if you're given the moles, remember, moles to grams, you multiply by the molar mass. If you have grams, you want to find moles, you divide by the molar mass. So 0.90 moles times 60.06 grams per mole. Right? I put 1 mole. 1 mole is per mole. Moles cancel. So it's going to be around what, like 50 something, 54 grams or something like that. 0.9 times 60.06, 54. I guess we'd stop there, right? Because they only gave us 2 sig figs here, so 54 grams. And that's your acetic acid. Okay, so notice, be careful. What I did, it's easy to lose a step here. Balance the equation, find the moles of the substance you're asked about from the moles of the substance you're given. So we figured out the moles of acetic acid from the moles of ethanol, right? They didn't give us the moles of acetic acid, they gave us the moles of ethanol. So you're using the balanced equation, you're multiplying it by that ratio, right? 1 mole of acetic acid divided by 1 mole of ethanol, ETOH for ethanol, okay? It's an abbreviation. So you do that first, after you balance the equation. Then you use the molar mass of the substance you want to convert that to grams. Why do we convert it to grams? Because we can't measure the number of moles. We can calculate them using that equation, but there's no way to verify that that's the correct answer. But we can use the molar mass. We know how much things weigh. We know how much a carbon atom weighs. We know how much an ethanol molecule weighs. We know how much a mole of ethanol weighs, a mole of acetic acid. By using that known value, 60.06 grams per mole, you can convert moles to grams. And that's often what we do in science. We use a conversion factor that we know. We put a lot of effort into figuring out that conversion factor. Speed of light is a conversion factor, right? So that's something people are measuring all the time. How accurately can you measure it? Because you're going to use that to figure out how far a star is from us or how far a galaxy is from us. That number is important, that conversion factor. Same thing here. We need to know the molar mass because that's going to allow us to convert between grams and moles. So a lot of effort back in the 19th and 20th century when they realized, hey, we got to know these numbers really well so that we can do this type of conversion here. If I didn't know this, you'd have no way to convert that, right? You wouldn't know how to get the number of grams. So that's why the periodic table is so important. It's our conversion factor to figure out the relationship between moles and grams, aside from other things.
Professor, sorry, I'm a little bit behind, but where did you get the 2 and the plus the 4 plus the 2?
So that's back. So go back and do section 3.4. That's how you calculate the molar mass of a compound. Yeah, you'll cover that in that section. Right, because 3.3 is balancing equations. 3.4 is mole and molar mass. So the acetic acid, you're gonna learn that, oh yeah, you need to know the number of carbon atoms. There's 2 of them. You need to look up their molar masses. You have 4 hydrogens here, so you're gonna add that 4 times its molar mass, 1.01. And then you got to do the oxygen. There's 2 oxygens, so there's your 2, and each one is 16, right? And then you're going to add.
Oh, so it just depends on how many there are of each.
Exactly. So like glucose. What's your major, by the way?
Biology.
Okay, so like glucose, right? C6H12O6. So here it would be 12 times 12.01, right? 6 carbons. 12 times 1.01. 6 times 16, right? And then that would give you 180.18 grams per mole. Yeah, exactly. So the number and then how much each one weighs. That's how you do it.
Okay. Yeah. Okay. Got it. Thank you.
Mm-hmm. Okay, let's see. Okay, let's do one more like this. So in this one, they're going to say that acetylene, which is C2H2, they tell you it's a gas, so we know it's a gas, reacts with oxygen gas. Now this one, I'm sorry, I misspelled acetylene. So acetylene reacts with oxygen gas to form carbon dioxide gas and water vapor. Okay, and then they give you the number, right? So then they say, how many moles of water will be produced from the reaction of 1.6 moles of acetylene. Okay, so same idea. We're just going to do the same calculation. This one we have to balance it though. This one doesn't balance, you know, it's not 1-to-1. Everything was 1 in the previous one. This one's going to have, am I right about that? Yeah, so let's take a look. So first you write the equation. So it tells you acetylene is reacting with O2. So those are your reactants. So reactant. And then they're going to form. Form is the word that we use to say it's going to produce. So those are your products. So this is a product right here, CO2 and water. That's a product right there. So 2 reactants, 2 products. It could be 1 reactant, 2 products, 1 reactant. Like, you know, if you blow up, what is it? TNT, for example, trinitrotoluene. That's a big explosive, right? It's used in a lot of explosives. It's only 1 reactant, right? It just blows up and then it produces a bunch of products. Same thing with nitroglycerin. It produces a lot of products. Okay. But you could also have one where you have a lot of reactants. So there's a reaction where you take carbon dioxide, you take water, and you take nitrogen and calcium and make some other 1 product, right? So you can do that too. But here we have 2 reactants, 2 products. So C2H2. Now, it's not essential for this problem, but I'm going to put the states of matter in there because we do need to know what they are if we're actually doing this. So it tells us these are both gases. And then it says carbon dioxide gas, carbon di, remember di is 2. And then water vapor. Vapor means gas. If it said liquid water, you would put liquid, L for liquid. But it actually says vapor, so that's gas. This is called an acetylene reaction. Acetylene is right here. Acetylene, when it reacts with oxygen, it produces such a hot flame that, well, it could blind you. It's so energetic, it produces ultraviolet radiation that could blind you, I think. But it also is so hot, it melts steel. So it's really good for melting steels at surfaces so that you can weld things together. It's really, really amazing reaction. Produces an enormous amount of energy. So let's balance it. We have 2 carbons on the left, but only 1 on the right. So remember, you change the coefficients, not the subscripts. So 2 carbons. Hydrogen's already done. 2 on each side. Oxygen, we have more oxygen on the right than we have on the left. In fact, we're going to have an odd number on the right. So let's do the oxygen. 2 times 2 is 4, plus 1 is 5. So remember what we said before, you leave the oxygen for the end. When you're doing these ones, this is combustion, leave the oxygen for last. Do the carbon, then the hydrogen, then the oxygen. That was back in 3.3. Now, we're going to have some number there, N. What is that going to be to balance it? Here's what you do. There's 2 here, so N times 2, right? So if N was 1, you'd have 2, and that's actually what you started off with. If N is 2, 2 times 2 is 4. So the total number of oxygen on the left side is just N times 2, or X. You could say X times 2. That's got to be equal to what we have on the right, which is 5, right? We already figured out we got 5. We have 4 here and 1 here. That's 5. So what do? You divide both sides by 2. And so now N is equal to 5 halves. So if you change that to 5 halves, it's balanced. Again, Alex, if it's asking you to write the balanced equation, it's not going to like that answer probably. It should actually, but I don't think it does. But it's now balanced. So we said if you want to have whole numbers, you multiply everything by 2, and that will get rid of the fraction. Because if you multiply this by 2 here, 5 halves times 2 is 5. So same thing. So multiply everything. 2 C2H2, 5 O2, 4 CO2. Multiplying everything by 2, and now it's balanced. It was balanced with the 5 halves, okay? But if you want to have whole numbers, that's what you would do, okay? So step 1, write the equation, balance the equation. Step 2, take the number of moles you're given. We're given 1.6 moles of C2H2. I actually, sometimes what I'll do is I'll just write it underneath the material so that I can see where the numbers are. 1.6 moles of C2H2. There we go. Then it says how many moles of water. How many moles of water? Okay. Very simple. If this is in moles, all you got to do is say every time 2 of these react, 2 moles, you're going to get 2 moles of water. So it's actually going to be the same number. So you take 1.6 moles of C2H2. The one you want, 2 moles of H2O, divided by the one you started off with, 2 moles of C2H2. So I'm putting the coefficients in, these numbers here. Units cancel. 2 over 2 is 1, right? So it's a simple answer. But now it's water, right? So let's think about our physical interpretation here. What this is saying is that because every time 2 moles of this reacts gives you 2 moles of that, the number of moles of water you're going to get is going to be equal to the number of moles of acetylene that you put in, right? It would be kind of like you said, I don't know. Oh yeah, like if you took apart a sandwich and I said, I don't know. Actually, that's not a good analogy. Yeah, that analogy works. But essentially what's happening is the number of hydrogen atoms you get in 2 moles is 4. And the number of hydrogen atoms you have in 2 moles of acetylene is 4, right? 2 times 2 is 4. So the reason that it comes out to be the same is that by having the same number of moles of acetylene in water, the moles of hydrogen are balanced, right? The acetylene has the hydrogen at the beginning, the water has the hydrogen at the end, so they've got to be equal. The hydrogen has to be equal to each other. So 2 to 2 is what makes that work out, okay? Now, Alex doesn't ask you to do this in this problem, but if it did, what you would do is the following. You'd say, if I had 1.6 moles of H2O, how many grams is this? You'd say, okay, 1.6 moles of H2O. How much does water weigh? Water is 2 hydrogens, 2 times 1.01, 1 oxygen, 16.00. Add those up, you get 18.02. So you'd multiply it by 18.02 grams of water for every mole of water. Okay, and that would give you the number of grams. Remember, moles to grams, you multiply by the molar mass. So 1.6 times 18.02, and you get 28.8 grams of water. Okay, so they didn't give us any grams in here, but I want to show you how it works out. This is something you can check later if you want to. Oops. Okay, so what we said that's 2, it was 5, right? Okay, I got that balanced right. 4 carbon dioxides, 4 carbons, 4 hydrogens on both sides, and then 10 oxygens. So there's your balanced equation, okay? So we worked it out that you put in 1.6 moles of this, and that gave you 1.6 moles of that, right? Because these numbers were the same, okay? Now we then converted it to grams, and we showed that this was 28.8 grams right there, right? So you could do this calculation for any of these materials in the equation. You could now figure out how many moles of the O2 reacted. So let me, just to kind of finish this up, let me do that. Let's say we want to know how many moles of O2 reacted. The ratio is 5 to 2. So you'd say 1.6 moles of C2H2. You want the oxygen, so times 5 moles over 2 moles. Okay, so to find the moles of one material from the moles of another, you use those coefficients. The one you want divided by the one that you already have. So 1.6 times 5 halves, you get 4. Okay, so now we could say this is going to be 4 moles. That's how much of the oxygen will react. Then you could ask, how many moles of CO2 are you going to get out of this reaction? We already figured out the moles of water, but how many moles of carbon dioxide? Well, same idea. Now you have a choice. You could actually use any of the ones that you have. You could use the 1.6 or the 4 or the 1.6, any of them. I'll use the 1.6 for acetylene just to be consistent. 1.6 moles of acetylene, you multiply that by the one you want, which is CO2. CO2 is a 4. And then C2H2 is a 2. So there you go. That's going to give you 3.2. Okay, so again, Alex is only going to ask you for one of the products, but you should be able to do all of them. As long as you know one of them, you can figure out all the others just because you have the balanced equation. And likewise, if I'd used the 1.6 for water, I would have got the same answers here too. It's all internally consistent, right? If I said, hey, 1.6 moles of water is produced, how many moles of CO2 are produced? Well, it'd be 1.6 times 4 over 2. 4 over 2 is 2. 2 times 1.6 is 3.2. You get the same answer. We can also convert all these to grams. So let me do your molar masses here. For C2H2, it's 2 times 12.01 grams per mole. That's the carbon. 2 times 1.01 grams per mole. That's the hydrogen. So that's 26.04 grams per mole. Okay. So for acetylene, if you have 1.6 moles, multiply that by 26.04 grams per mole, right? Multiplying by the molar mass converts moles to grams. It's a very simple calculation. So 1.6 times 26.04, you get 41.7 grams of C2H2. 41.7. Okay, so 1.6 moles of acetylene corresponds to 41.7 grams of acetylene. That's how much it would weigh. That's its weight, okay? What about oxygen? Well, oxygen, we have 4 moles. And oxygen is 2 times 16, right? That's the molar mass. So that's 32 grams per mole. Okay. So now if you have 4 moles of O2, multiply that by your 32 grams. That's going to give you what? That's going to give you a lot, right? 128, 64, 128 grams per mole. So I'll just write down 128. So actually, when you're burning an acetylene torch, the oxygen's coming out of the air, right? Look how much oxygen is actually required to burn that acetylene. You look at that flame, right? You got this torch coming out here, and you got this flame that's burning. Essentially, the oxygen is coming from the air, and then you have a little tank. The tank has the acetylene in it. So that tank and the air is going to mix, and that's going to give you your flame coming out of there. Okay, so there's your mass ratio, right? So the mole ratio is 1.6 to 4. The mass ratio is 41.7 to 128. Okay, we got one more, which is the CO2. So let me just do that down here. Again, this is not requested in the ALEX problem, but it's important to be able to do this because the ALEX is just testing you on one of them, but you can do any of them is my point. And we often want to know more than one. Okay, so let's do the CO2. We got 3.2 moles of CO2. That's what we're given. Okay, well, how much does carbon dioxide weigh? Molar mass. There's 1 carbon and 2 oxygens. So that's 44.01. I know that one offhand because we use it a lot. So there's your molar mass of CO2. Carbon, 2 oxygens. Now you say, okay, we got 3.2 moles. We're going to convert it to grams. So multiply by the molar mass. Okay, so it's going to be a big number because carbon dioxide relative to the other gases is pretty heavy. It's 44.01. So times 3.2. And you get 140. I'm going to round it to 141. Okay. You could test the law of conservation of mass. Remember what I said is the mass of the reactants that actually react has got to be equal to the mass of the products that are actually formed. So the mass of the reactants are these 2 numbers here. So it looks like you've got, just kind of adding those together, 41.7 plus 128. It looks like it's around 170. And then if you add these together, 141 plus 28.8, round that, you get 170. Isn't that cool? So the mass of the products is equal to the mass of the reactants that actually reacted, 170 grams. So you can actually test that, right? You could say, hey, I'm going to put in these masses and see what the masses of the products you get out. And they should be pretty close to each other. All right. So notice what we're doing. We're putting everything together. We're taking the balanced equation that we learned in section 3.3. We're taking the moles and mass and molar mass that we learned in 3.4. And we're combining those 2 topics. The balanced equation tells you how many moles of each substance you're going to get one from the other. And then converting it to grams, that's your molar mass calculation. You multiply by the molar mass to get the grams. There are other types of problems that you'll see in Chem 11 where you take the number of grams and you convert that back to the number of moles. So then you would just divide by the molar mass. That's why we did that in section 3.4. Okay. So next week, we will cover 3.7, which is the last topic of chapter 3. It's called limiting reactants. Okay. Now that's actually, you know what? There's a lot in that section. So we not only have to do the limiting reactant problem, but we also have to do theoretical yield. So, so I will cover that next week, but you should be good all the way up to the last section. So you should be good all the way up to 3.6. And reach out to me this week if you have any questions, and enjoy the rest of your week. And I'll see you next week. Take care.